So for all these, your loads will be pulsating, and what has been observed is, that your number of cycles is purely, I mean, is basically this plot SN curve is plotted between the stress amplitude, okay, and number of cycles. So what it says is, the moment your stress amplitude keeps going low, okay, keeps going low, your number of cycles increase, okay. And you would see that now you would say that why here no mean? Because this plot, typically SN curves are typically, okay, SN curves are plotted using 3-point beam bending, and they are plotted for zero mean. Okay. Now you have SN curves available for some positive mean and negative mean also, but typically the SN curves which you get are for zero mean. Okay. So here it's a zero mean, and what you say that for zero mean, stress, when I say zero mean stress, what it means? Let's say the maximum stress is plus 10, and the sorry maximum strain is plus 10 and minimum strain is minus stress is minus 10. Okay, so plus 10 to minus 10, the mean will be summation of that divided by 0, which is 0. The mean is going to be 0. Okay, and the amplitude is going to be what? 10 plus 10 by 2, which is 10. Okay, so you have amplitude as 10 and mean as 0. Okay, sorry, this 0 is not looking like 0. So okay, so what people have observed is, the moment this 10, okay, if your stress amplitude is going down, if it is going down from 10 to, let's say, 1, you will see a significant improvement in your fatigue life. Okay, and there are materials like steel, typically steel, for which they say that this SN curve becomes asymptotic. Okay, okay, so what they say that this reduction in stress with respect to life, or this curve becomes flat, okay, after some number of cycles, or rather I would say below certain level of stress. Okay, so it may happen that, let's say, this stress for steel is 3. Okay, so they may say that for 10 megapascal to 3 megapascal, the life will increase, but the moment stress is below 3 megapascal, we can assume that the life is infinite. Okay, so any stress amplitude which is 3 megapascal for steel, okay, may give you infinite life. Okay, but do all materials exhibit this? No. Like aluminum or other materials, exhibit this curve. So for that, what happens is, so let's say here you see this red curve. Okay, this blue curve is typically exhibited by steels. Okay, but this red curve is typical behavior of aluminum. So for aluminum, this curve will not become flat. It will not become parallel to x-axis. Okay, and what it means is, it means that the the reduction in stress will further reduce your life. Okay, the life will not go infinite below any stress level, any stress amplitude level. So in that case, what you typically say is that anything which is above, let's say, your endurance limit you define with respect to 10 to the power 7 number of cycles. Okay, so you say that, okay, if my component meets 10 to the power 7 number of cycles, I can still claim that it has infinite life. Though in reality it does not have infinite life. It may have life which is 10 to the power 9, let's say. Okay, if this graph, okay, let's say here it becomes 0 at 10 to the power 10. My life may be 10 to the power 10, but as it is above 10 to the power 7, I can still say that, okay, it is meeting infinite life. Okay, so okay, now let's move to how you estimate your fatigue life. So typically, if you see this SN curve for steel, it may look like this. It becomes kind of flat. So you can say that, okay, beyond this level, anyway, it is infinite life. But I want to calculate life in this region. Okay, so you have Baskin's equation. Okay, so this is the Baskin's equation. What it says is, now notice that here it is SR. Okay, so this SR is equivalent stress amplitude. It is not stress amplitude at means at zero mean. It is equivalent stress amplitude. Okay, so equivalent stress amplitude is A times number of cycles to failure to the power B. Okay, and you can see here, if you take log of both the sides, you can calculate these constants B and A. Okay, okay, here they have assumed that, okay, this is endurance, this is stress amplitude at your zero kind of number of cycle, okay, which is 0.9 SUT typically for steels again. Okay, so this equation, from this equation, once you have this constant A and B, you can get to know the number of cycles. Okay, but one thing what okay, maybe this curve is something which I will I'll not go in more deep, but what you, the important point here is what you have to know is that all these fatigue calculations are there to estimate the life for crack nucleation. So this curve, it does not really give you the life for final failure. Okay, it only gives you a life for crack initiation. Now you may say that that's okay because it is conservative. Yes, it is conservative because it would let you know that, okay, the crack is going to initiate, nucleate or not. Okay, after crack nucleate, will it lead to failure or not? It does not tell you. There comes fracture mechanics, which is out of our today's talk, maybe mostly. Okay, so that you have to be very sure that these are calculations are there to estimate life for crack initiation. Okay, now one thing is, I told up till now that this life, whatever SN curves and this are there for zero mean. Now what if your mean is not zero? So one thing to see here is, okay, here what you see, these three things. So it will show you when your mean is zero. Okay, so this is what this is zero mean. As you see this line, you have positive and negative same. Okay, now this is compression, as in you are operating fully in your maximum stress is -10 uh, and minimum stress is -30. Okay, so you're operating in fully compressive zone, and here you are operating in fully tensile zone. Okay, so it's zero mean. So what they have, sorry, positive mean. So what they have observed is, as your mean stress increases, note here sigma m4 is maximum. So you see the SN curve is lowest, as in if your mean stress is very very high, okay, your tolerance is very low. How much you can only absorb sigma A, let's say sigma A4, you can only absorb this small stress amplitude, sorry. Okay, so for this mean of sigma M4, you can absorb sigma alternating 4, only this level. Okay, but if you have very low mean, let's say sigma M4, for this mean, how much you can absorb? You can absorb huge stress amplitude with respect to sigma A4. Okay, so what it says is that for sigma A1, okay, the stress amplitude may be 50. Okay, but for sigma A4 only you can absorb stress amplitude of 10. Okay, so what it shows, the moment your mean stress keeps increasing, your ability to absorb fatigue loading decreases. Okay, so earlier if you're with zero mean or higher mean, your component may fail much earlier than negative or lower mean. Okay, for same stress amplitude. So now how you do it, as I told you, okay, in in that calculation, earlier calculation of Baskin's equation, what you do is you calculate a equivalent amplitude. Okay, and that is done using Goodman line. I'm going to cover Goodman and other mean stress corrections. Okay, so what it does is, for zero mean, okay, your amplitude was something. Now if you have to calculate your amplitude for some given mean. Okay, this is your mean, this is average stress, or this is mean. So for this mean, your stress amplitude, effective stress amplitude is going to be this. And now this stress amplitude you put in this equation to get number of cycles. Okay, so like Goodman, there are typically Goodman and modified Goodman are mostly used again. You know, a few people may use Gerber's parabola also. Okay, which is which is little less conservative, I would say, because it allows higher mean. So let's say what it tells you is that for this amplitude, Goodman allows this mean, or rather for this mean stress. So this Goodman line is infinite life line. Okay, it means that below that, as far as you are within this, you will have infinite life. If you are above this, you will have non-infinite or finite life. Okay, so for this magnitude, this mean stress, Goodman says that you can manage to with this amplitude, stress amplitude also, in order to have infinite life. Okay, the maximum limit. But what Gerber says that, okay, for this mean, you can, Gerber, here the intersection is here, right? So for that mean, Gerber says that you can cope up with little higher magnitude also. So, sorry, this is A. This is Goodman's A. And this is Gerber's A. Okay. So that way you can say that Gerber's parabola is little less conservative, but Goodman's is more conservative. Okay. So these are just ways, to give you a, a good overview of how much mean can be accommodated for infinite life. What is the limit of mean or amplitude, with respect to mean and amplitude, how they both of them are related. Now if you want to have factor of safety, as you may see here, ng. Now factor of safety, or safety margin rather, what you say is, okay, now if my factor of safety is 2, it means that my line is lifted here. Sorry. I'm wrong. The line is here. Okay, because I want 2 factor of safety, right? So my whatever my this limit is now should be half of this limit. Are you getting it? Okay. So my Goodman line becomes further inside and I become more conservative. The reason I become more conservative, because I want to have higher safety margin. Okay, I'm assuming here as 2. Okay, the moment you keep increasing safety margin, the more and more you go inside it. Okay. Now, okay. Now, interesting thing is all these calculations were for constant amplitude. Okay, but what if you have varying amplitude? Now you may ask me, why varying amplitude? Okay, see, varying amplitude typically, if the aircraft cycle, or even let's say I take a fuel tank example itself from truck. Okay, you may have fatigue loading coming from engine, which is still let's say plus 10 to minus 10, just fictitious numbers. Okay, just neglect these numbers, plus 10 to minus 10. Okay, now you get road vibrations, and let's say that the phase is same, and you kind of overlap your engine vibrations, and now your vibrations become okay, you have now plus 20, okay, to minus 20. So what you have? You have plus 10 to minus 10 here. Okay, you have plus 10 to minus 10 here. And you have now, this doesn't appear plus 20, but let's say plus 15. Okay, so plus 15 to minus 15. So what is varying? The amplitude between these two loads are different. Okay, here you have 10 amplitude and then you have 15 amplitude. Okay, so what you do, can you really calculate fatigue life for that? Yes, you can calculate, but the process is little different. What you try to do is you try to calculate the damage for the fatigue life cycle which has amplitude of 10 and the damage for fatigue life cycle which has amplitude of 15. Because as you see in SN curve, okay, the fatigue life for this is this and fatigue life for this is this. So will you take average of fatigue life? No, that is not the method. Rather, what you do is you calculate damage at this amplitude and you calculate then damage at this amplitude. And so on, you calculate damages for all those amplitudes, small amplitudes, and you equate them with 1. Okay, why 1? Because if the factor of safety is not there, okay, if factor of safety is 1 or rather, then your limit is that your damage, okay, total damage can be only 1. It cannot exceed 1, or rather you can say that your at your stress, these are the number of cycles. N1 is the number of cycles which your component undergo. So let's say your bracket undergoes 10,000 cycles, okay, total 10,000 cycles. Okay, now you have 5,000 cycles at this amplitude, okay, and 5,000 cycles at this amplitude. This pointer is painful. Okay, so you have 5,000 cycles at n1, and you have, sorry, you have n1 as 5,000, okay, and you have n2 as also 5,000. Now what you say is your capital N1 as in number of cycles to failure for amplitude of 10. You get from here amplitude of 10 has number of cycles to failure. This is n1. Okay, and what is n2? N2 is number of cycles to failure at an amplitude of 15. Okay, so what you do, you calculate your number of cycles to failure at amplitude, higher amplitude, which is 15. Okay, so now you have n1 5,000 divided by n1, which is number of cycles to failure at lower amplitude, and n2, which is at higher amplitude, you divide by number of cycles to failure at higher amplitude. Okay, and you try to make sure that this ratio, summation of all these damages or ratios of n's is equal to 1. Okay, and this is something which is also known as minus rule. And note down that this is linear. Okay, this does not account for any order. I mean, whether the higher higher amplitude is before or after lower amplitude. Okay, so this is minus rule. Okay, now people may ask you, okay, now you have certain fatigue life, how you improve your fatigue life? Okay, so typical industry wide methods are, is how do you recollect? I mean, we talked earlier that your negative mean will increase your fatigue life. Okay, so how you induce your negative mean? Negative mean is nothing but inducing negative residual stresses. Okay, these negative residual stresses are really very important if you want to increase your fatigue life. So what they do is, one very commonly used method is short pinning, where you have one gun which has, small metal balls, and those metal balls, gets impinged on the surface, and that's what you know as you call as short pinning. Okay, so they kind of introduce residual stresses, negative stresses. Okay, and second way is, you overload your component beyond yield point and then unload it. Okay, so the residual stresses will be negative. So these are the two ways, which will improve which will bring your SN curve up, I mean further up, and improve your fatigue life. Nageshwari, I think
Yeah.
I think I'll skip this strain based approach, because I'll quickly cover rather uh, this packages and random vibration, okay, for the benefit of audience. All
Okay.
right, okay.
Fine then. See, we do not have any time constraints. So if you want to cover the complete session, we are completely fine with it.
Is that okay for you? Then I
Yes.
can. Okay, 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 guys. So let me also cover this strain based approach. Why you have strain based approach? See, typically when you have this curve, this number of cycles to stress amplitude. Okay, if you plot it from 0, number of cycles to 0, okay, what you see is in this zone, okay, and this zone it may be high cycle fatigue, which is, let's say, typically above, 10 to the power 5 or 10 to the power 4, okay, but this zone is low cycle fatigue, okay, and this is high cycle fatigue. So what they say is high cycle fatigue is stress dominated, okay. The reason, you may recollect that, the stress strain curve also goes like this and then goes like this, okay. So in this zone, okay, the stress is something, with respect to your strain, or strain, or you can plot this as a deflection also, or this is, either force, or you can plot this as a stress also, okay. So what happens, primarily stress, so what happens, as far as the material is in linear portion, I mean linear zone, the stress is proportional to strain, okay, and you see the same increase in stress with respect to strain, okay. But after yielding, or as it enters into plastic zone, the stress does not increase much. What increases? It is strain which increases significantly, okay. And typically all the high cycle fatigue lies in this zone, SCF. Okay, and low cycle fatigue is typically when you exceed your yield stress, you enter into plastic zone. Okay, and here, now what you think should be deciding criteria? It should be strain, not stress. So the algorithms which work here, they are called based on, they are based basically on strain. Okay, and the algorithms which are for SCF, they are based on stress.